Right, so I thought I'd start off by just showing you the quick setup that I've got going here, just to put into context all the things we want to test and how we want to do it. So what I've got a power cord coming in, not plugged in at the moment, all safe. I've got it going through a bit of a connector block just to keep things all neat and tidy and safe. This is not what I would use in the production version, but it's going from there into the transformer. This is a 12 volt 80 VA, and there's two coils in here, so 160 VA toroidal transformer. From there I'm taking the taps out. I've connected the center taps, or the two together, and that's my center tap. From there we're going off to our original bulk capacitance board. We've covered this one in the past video. I've got my bridge rectifier diodes down the bottom. Just after the bridge rectifier diodes, I take it through a inrush current limiting board. Remember the first video was a bit of a catastrophe, so I added this. This relay is closed, which short circuits which then short circuits the inrush current limiting resistors. So they should only be active for the first 2 seconds after power on, just to give the caps a chance to charge up a little bit slower, to not put that much strain on the diodes. I've also changed the original diodes to slightly more beefy diodes, so strictly speaking I shouldn't need the inrush current limit board, but I thought it was a nice and tidy addition to the process. So I'm going to leave that in there. There's our connector block going up to our through the full stack, apart from the bulk capacitance board. Through the full stack, and that's effectively my data bus. You'll see I haven't populated it now because it's not relevant to the test we want to do today. So out the back end of the bulk capacitance board, we're getting to running it into the main power supply board. So the reason I call this the main power supply board is this is the board that will actually control all the voltage and the thing coming out. So what you see I've done here is I've actually populated the bare minimum amount of components on this thing to actually run some initial tests on, and I think it's probably because of my first board catching fire the first time I turned it on. I figured let's sacrifice as few components as possible to do the initial testing. So I've really just populated those. What you can see there, that's my current shunt. So effectively these are 10, you'll see there's 5 over here, 5 on the other side, so it's altogether 10 0.1 ohm 1% resistors sitting there. So because the reason to do that, obviously, as we've discussed in the past, is to limit the amount of wattage or heat that each one of these individual components need to dissipate. So through the 10 of them at a quarter watt each, there's more than enough to pull the 3 amp all the way through here without any big issues. From the initial shunt resistor pack, we go through to the op amps. So I'll go through the circuit in a moment. From that op amp through to this op amp, that's our just a normal 10 times 10 differential amp. Through here we start coming in with the voltage and the current set. So you'll see these two, as I've shown before, these are our analog connections, so you can put a pot onto these and manually or set these via analog, and those two would effectively drive the op amps into the correct way. From there on, this is our current source, 10 microamp current source configured with that resistor. The reason for that is obviously to keep this guy's minimum current delivery up and going, so that we can get it all the way down to 0 volts, so setting it between 0 and 30 volts. That's the purpose for that one. There's some diodes. I've got some, there's another one on the back end, which we'll see in the circuit now. We've got bypass caps at the bottom of these. This is a dual loaded board. I'm not going to show you the bottom side right now. But yeah, that's the setup. And ideally, so one more thing I thought I'd quickly mention is that you'll see there's a relay here that is not populated, and the purpose behind that relay was to allow me to pull from the lower, so the 17 volt rail, as well as the 30 volt rail, to minimize the heat dissipation through this linear regulator, the LT3080 we've got here. And the reason is obviously that when you are below like 12 volts or 15 volt maybe, you'll actually, this relay will be clipped over to this rail, and it'll only have to dissipate the rest of the voltage up to 7 volts. So if I'm putting 15 volts out the back end and I'm reading it off the 17 volt rail, I only have to dissipate the other 2 volts in here. If you had to do that, you'd be dissipating almost half the full voltage in this device, and it'll just get a lot hotter. So in this configuration, as it stands right now, it should be relatively safe to turn on. The main voltage coming in here, the 30 volt, is actually connected to the center connector there. This one then is connected to there, and this rail is connected to the upper 2 pads. This rail is connected to the bottom 2 pads. The center pad is actually the input to our voltage shunt our shunt resistors there. So it should be relatively safe to turn on right now, as it's not really connected too much. There is, however, the power rails for our op amps are actually connected in, so you know as well as the main voltage for, so not the main voltage, the VCC voltage for LT3080, not the regulating current, regulating voltage. That's actually disconnected at the moment. So that's where we are at the moment. So let's quickly have a quick squiz. What I'll do is I'm going to turn on, or just set this little cheap current meter there. Let's just have a quick squiz, how much current that draws, and let's plug it in and see what happens. Connecting now. Right, nothing seems to have caught on fire yet. 230 volts. Yep. 12 volt side, still AC. Let's drop that down. We should be able to drop it to 20. So there's our 13.75. That's RMS, obviously, and the same on the other side. And if we measure over both, we should be getting. Oops. Yeah, because we should be getting 30 volts out of that. Yeah, there's our 27 volt. Right, let's go to this end and see what we're getting here. So now we should be in DC. Let's flip that over to 20 volt, and on that tap there we should be getting 17 volt. Nice. And yeah, and correct. And if we flip that up to slightly higher, we should be getting 34 volt out of that side. Awesome. So far so good. So as we can see, there's our ground tap in the middle, and our 17 volt rail, 17.1 volt, and our 34 volt rail, 34.3 is what I'm getting. So that all, it seems quite good. So if we stay on our ground panel here, success. I think that is a successful first test. We've not set anything on fire. Everything seems fine. Let's go to our schematic. So there's our schematic. Okay, so if we follow this line, oops, and highlight the line, go over here, and then we can see we are connecting through power amp that LM358, op amp this LM358, and the back top pins of our board. So let's do that. Let's confirm that we're getting voltages there. There, 34 volt, awesome. As well as this guy there, 34 volt, as well as our back. So it's going to be a bit of a stretch. and 34 volt there. So all that seems all good. Right, so the next step, I promised I would video this first time, because last time we had nice fireworks and I missed it, and I said I would do this one for us and make sure that we don't miss it again. Okay, as expected, he's not hot because he's not doing anything. The set voltage on this thing should be 0 because there's nothing connected over there. So it should be turned off and not be dissipating any power. We're also not drawing any current from the outside, so that should all be good. I'm going to wire in some pots on these so that we can start doing something. I might solder a quick link over those two connectors just so that we are connecting it to at least one of the two rails, and we can start testing some more. So what you're looking at now is an Arduino Mega. I just configured it to, I wrote a quick little app just to do PWM pulse width modulation out of pin 5 and 6 actually. I want to use that to test the power supply board we've done so far without me needing to put pots and all kinds of, build up the rest of the circuit. As I said last time, I wanted to make put on as fewer components on there as possible at this stage. So here's our Arduino. I've built a quick little RC filter to just take the edge off some of the square waves. It's not a fantastic filter, but I'll quickly show you guys what it does. So on the screen I've got my oscilloscope set up, 500 microseconds per division. I'm measuring the average DC voltage over the entire scope. At the moment it's essentially 0. So if I output, let's say, a voltage, and I've literally done no work on this. I've gone from 0 volts, which turns the PWM off, which is what it is in its default state. I can turn the voltage up to 153, which I worked out should be roughly about 3 volt. And you'll see the average voltage there coming up to about 2.8. So a little bit of calibration still required. And what I've done is I can also set both PWM 5 and 6. So if I set PWM so if I put 6, which is which I haven't captured on the scope right now, to let's say 50, which I think is roughly about 1 amp, and I do the voltage, and I can set that to 100, that comes out to being 0.98 amp, so the PWM will be adjusted similarly, and the voltage is now sitting at 19.61 volt, which effectively gives us an output at this point of it's still coming down there, but yeah, 1.9 volt, which through the times 10 amplifiers on the PSU should go up to 19 volt being sent to the set pin of the LT3080, which should then effectively be outputting 19.6 volt, or in this case 19.23 volts. So remember, this is just a rough test to see if at least what I've built so far actually works. I'm not super calibrated or worried about the precision or the accuracy at this stage. Okay, so I have my Arduino with the two RC low pass filters on here. One is connected to the analog VREF, or sorry, VSET pin over here. The other one is connected to iSet. These are test points. Remember, as I suggested, you can connect normal pots on there. I figured I was going to control this thing via a microcontroller eventually anyway, so we might as well do that. In the production version, these will not be populated, and they will actually be VSET and iSet will actually be driven via two digital to analog converters. One is sitting over there, MCP 4716. One over there, VSET and iSet, respectively. So I've got my Arduino powered on. I've got my two RC filters connected through to the analog measuring point here. These incidentally go straight through to the same connections as the digital to analog converters, which will eventually sit over there. So effectively we've just got quite a bit lower resolution signal feeding in there. The signal from here wasn't fantastic, but let's see how it goes anyway. I effectively just want to measure that there's something coming out on the outside. If we look at the circuit schematic, I have now, as we discussed, rigged up the iSet and the VSET lines here, going straight through the actual analog test points here, where you can just connect a pot if you wanted to. I didn't want to do that. I'm effectively simulating this a little bit crudely straight from the Arduino PWM with a RC filter on it to just smooth it out a little bit. Similarly with iSet, it's coming from there into our iSet line. So looking at our board layout, again, if we just go back here and we highlight this line, right, we can see that it is the iSet analog line over there. And if we highlight the other line, the VSET, it is just the other item there. Right, so let's look at what I've got on show here. And you'll see that I have put this jumper on just to simulate the relay. That'll eventually come in. And we are feeding in from our RC filters, VSET and iSet, coming in here straight from an Arduino Mega. That's running a very simple sketch, and let's start up a com editor here, a serial monitor, and let's plug in our Arduino and see how that works. Okay, and wait for it. Let's see what happened to our Arduino. Tools. Let's maybe restart our com editor. And there it is. Right. So there's our com editor, or serial monitor at least. So there's our serial monitor, and we've got the initialization, and I'm just going to initialize it. I know it does. I've actually checked. It does initialize the PWMs to 0, but I'm just going to, for safety's sake, I'm going to set them both to 0, and off we go. Right. Let's turn this guy on. We can see him clearly. And he's monitoring the output voltage that is being fed through this. So given that I'm feeding, or pushing this thing from the lower levels, we should probably not go above 12 volts on this one today. And given that we only have one of the LT3080s apart from, as opposed to the 3, we should not be going above 1 amp if I didn't want to load it down. But I'm probably going to set this to like 100 milliamp and then just see if I can regulate the voltage at all. As I said, this is very, very crudely done. I just want to see if that works. If that works, I'll go ahead and build the rest of the circuit up. Okay, let's plug it in and see what happens. Okay, we're in. I'm not quite sure why we are measuring 0.71 volts. It might be a little bit of noise on the PWM lines, but let's see if I up the current to, let's say 2, what are we getting? I 3. That's not a good sign. It feels like something is more excited than it should be. Come on. I'm just going to power down my Arduino. 5 volt. Where are we seeing this now? Tools. Monitor. There we go. And we're back down to 0.7. So I 0 V 0. Okay, and we're setting that. So let's do I 5 and V 10. Awesome. Awesome. That's exactly what I was hoping for. So if we say, let's just set the voltage to, what was it? 10. Let's make it 15. We're getting, we're supposed to, wow, the calibration is way out. I should be getting about 3 volt out. And getting 4 volt out, but okay. I'll put that down to the RC filters not being the smoothest things in the world, and you know, generally this is not the setup that we want to go with. But the point being is that I can set the voltage quite nicely. So if I go to 17, for instance, that goes back down, yeah, to 4.5 volt. And if I do it again and I set it down to, let's say, 12, 3.3 volt, it should be 2.3 volts, so okay, I'm fairly sure we can do, that's probably because there's no load, etc. So I've actually ordered a dummy load, I've actually ordered a board from Osh Park, where I've created the dummy load very similar to what Dave Jones did on the EEV blog. So as soon as that comes, I'll build that up and we'll actually have a decent dummy load to run. Right now, if I wanted to test that, I would have to just put a resistor or something on there, and I didn't want to really do that without being able to monitor the current nicely. But I think that is a relatively successful test. I don't want to push it much higher than 5 volt. Let's see if we push it to 20. That's giving us about 5.2 volt. Let's say 15. Correct. Sorry. That should be V25. And we should be pushing about 6.5 volt now. V30. And that should be, that's pushing 7.5 volt. V35. Ooh, we're a bit. Ooh, I'm gonna turn that down. 10. I'm just a little bit worried that I'm putting too much. Now what is happening now? Alright, that's a bit weird. So I've set the voltage down to 0, the current down to 0, and it's come down to 8 volt weirdly.